Hi, this is Professor Fernandez. In this video, we're going to work out an example of the direct comparison test. So this example comes from the Lecture 7 notes from the course that it comes from, which is Calculus 2. You can find those notes on this website and all these other goodies. Okay, so let's take a look at the example. It says, use the direct comparison test to show that the series below converge. So we're actually told that they converge, and we're just asked to use a specific test to show that they converge. So I'm going to walk through how to do this and make reference to the actual direct comparison test itself because it has some assumptions that we're going to have to check. But the first thing I'm going to mention is, the workflow for doing this. So first thing you want to do is take a look at the series and see if there are any terms that can be removed. For example, if I look over here, I can probably get rid of the +1 and maybe generate a new series, right? Look to see if there are any terms that can be removed or if the series reminds you of any other series as a way to get going and start the process of finding that new series that you're going to compare this one to. Okay, so I'll vocalize my thought process when I look at this series. So I look at the series and I first see the cosine squared of n. And that makes me think of cosine, which makes me think of oscillation, and then oscillation between -1 and 1, right? So oscillation between -1 and 1. And then my brain latches on to the 1. So I think, oh, this is like 1 over n squared, right? So the series that I'm going to start off comparing this to is 1 over n squared. Now I wrote approximate, right? For some problems, it may be a very loose approximation. I actually don't know what the sum of this series is. I do know what the sum of this series is, and I know it converges, but I actually don't know whether this sum is close to that sum. But it doesn't matter, right? For the purposes of the direct comparison test, we just want to prove convergence, not compare the sums or derive the sum. Okay, so that was the first step in the procedure. Figure out through some method, and I talked about it a couple minutes ago, a new series that you're going to compare the given series to. Second step in the method is hopefully the new series that you're going to use for comparison purposes, you can show converges or diverges fairly quickly. So in this case, this is a p series, right? Remember, those look like 1 over n to the p. And therefore, p here is 2, so p equals 2, and that's bigger than 1. And that matters because that is the activation condition for convergence. So I'll send you over to the Lesson 6 lecture notes in this course to get a little refresher on p-series. So we now have information that we are going to use, right? We know that the series that we're going to compare the original series to, we know that it converges. And then let me just discuss intuitively now, this is not part of the solution, but intuitively now what's going to happen. So if we can show that cosine squared or n over n squared is less than or equal to 1 over, leave myself some space here, 1 over n squared, if we can show that, and we can show that these terms are all positive, or at least bigger than or equal to 0, then what's going to happen? Then basically you can see intuitively if I sum all of these terms, right, from whatever to whatever, in this case n starts at 1 to infinity, then this one, because it converges, has a sum, right? It sums to something. So then, therefore, that's going to imply that this one is going to converge. And that's basically the direct comparison test in a nutshell. And notice the procedure that I just used is exactly the workflow that we are going to continue beyond this second step we've already done. That is to say, going back now to the solution, right? We are going to have to show that because we think this series converges, we're going to have to show that its terms are less than or equal to the terms of this series. Okay, so to show cosine squared n over n squared less than or equal to 1 over n squared. How do we do that? Well, this is already containing a hint of what to do, right? You could work backwards. So I'm going to do that just for the purposes of illustrating how this works and then giving you some practice with inequalities. And then I'll go back and actually write out the quote formal illustration of this inequality. So what would I do? I would say I'm going to start with the thing I want to show, which is generally not something you want to do in a math class, but again, we're learning here, so I'm going to start here, right? And then I'm going to say multiply both sides by n squared. Remember how inequalities work? If you multiply by a negative number, it switches the inequality. We're not doing that here. N squared is non-negative, and n is starting at 1 anyway, so we don't change the inequality when we multiply by n squared. And then I get here. And then in this particular case, I have to ask myself, how do I show that? Right? And the answer is that cosine squared is cosine of n squared, right? And remember that I already know that cosine of n, or cosine of x, doesn't matter, oscillates between -1 and 1. So if I square it, right, it's going to oscillate between 0 and 1. So those are the smallest and largest values of this function. So for sure, it's going to be less than or equal to 1. So I've started with something that I wanted to show, and I've ended with something that I know. So here is now the formal way to do this. You would start by saying, oh, cosine squared n is less than or equal to 1. And insert here everything I just said, some version of the graph or, some other argument for why this is true. And then I'm going to divide both sides of this inequality by n squared. Okay, doesn't change the inequality. Again, I'm not dividing by anything negative. So, and then there we go. That's it. I'm back to what I wanted to show here, was to show this, and we did it over here. So that's just a really quick, and we'll do this again for the second example I'm going to do in a minute, way to handle this part of the direct comparison test, showing the inequality between an, the series you started with, and bn, the series that you generated. All right, so now that we have that, we have those two parts done, so an less than or equal to bn. The last requirement of the direct comparison test is to just double check that all the terms are positive. So indeed, cosine squared, or non-negative, cosine squared n is non-negative. It's never equal to a negative number, and neither is n squared, and neither is 1 over n squared. So indeed, we have 0 less than or equal to an less than or equal to bn. I'm scrolling here because this is the actual statement theorem of the direct comparison test. Again, comes from lecture notes in lesson 7 in the course. And so we've verified all the hypotheses. We had two series. The bn for us was the 1 over n squared series. We know that converges. We've verified these hypotheses. This one is not so strict. It doesn't really matter too much if the an can have terms that are 0, as is the case when we're looking with cosine n squared over cosine squared n over n squared. So we verified that, and then we get the conclusion. So an converges. This is our an series. So I'm going to scroll back up here and say, great. So conclusion, this one converges, which is part of what we wanted. Well, what we wanted to show, right? The original prompt showed that these series below converge. So that's part A. So now I'm going to go off and do part B and speed things up a little bit to give you some more exposure to the direct comparison test. Okay, so remember the first part of the procedure that we did. We were coming in here, we were looking at the series, and we were trying to figure out if there's another series that it reminds us of. So, especially because here of the 1, we can think about n getting larger and larger, and eventually that plus 1 not mattering so much in relation to the 2 to the n. So we're going to compare this series here to n equals 0 to infinity 1 over 2 to the n. This is, by the way, the same comparison that we did in video 7.1 in this series. That was a video about the limit comparison test. So very, very similar to the direct comparison test, but a little different. There you use a limit to determine convergence, divergence. Here we're doing a direct comparison using inequalities. Okay, so that was our first step, right? Remember that. Second step is now, do I know anything about the convergence or divergence of this series? This one happens to not be a p-series, but it is a geometric series, right? So I can write it that way. Geometric series. The a value here is 1. The r value here is 1/2. And since the absolute value of r is less than 1, that tells me it converges, right? So take a look at video 6.2 if you want a refresher on geometric series convergence. That was all about, that video was all about that. So we know that the series now converges, the one we're comparing it to, right? This is our bn. So now looking at our AN, we're going to run through the checks, right? Hopefully we can get this inequality set up. And then I will know by the direct comparison test that the series AN, because it's less than or equal to the series BN, because this converges, that will converge. Okay, so now let's set up our inequality. Let's just write it down. First of all, the AN is 1 over 2 to the n plus 1. The BN is 1 over 2 to the n. This is what we would like to show. Okay, this one is pretty simple and straightforward because all of these terms now are positive, right? Nothing is 0. These terms are never equal to 0. So in fact, we can show something stronger. We can show that, right? They're all positive. Great. So it's really always about this side, the AN less than or equal to BN side. Okay, so how do we do that? Again, we can work backwards here. We could start off with the thing we want to show, and then we could manipulate it down to something that we know. In this case, maybe we take the reciprocals of both sides, right? And that would give us, changing the inequality sign, that would give us this. And then we subtract, we don't have to subtract one. Really, at this point, we figure this is the same thing that's over here, except the left-hand side has a plus 1. So it's always going to be bigger. It's like saying, x plus 1 is bigger than or equal to x. It's actually always bigger. It's 1 more, right? So we've done what we did before. We reduced what we want to show to something that we know, right? So now to do it more formally, we would go the opposite way. So we would say, start with the fact that 2 to the n plus 1 is bigger than 2 to the n, right? That's true because the left-hand side is 1 more than the right-hand side. And then take the reciprocal of that. Okay, when you take the reciprocal, it changes, flips the inequality sign. There we go. And, lo and behold, this is exactly what we wanted to show. So check, right? So this is now the AN less than or equal to BN. Again, in this case, it's less than, bigger than or equal to 0. Also, in this case, bigger. Check, right? So we did that check, and then we go back to the direct comparison test. And we just run through, make sure we checked everything we needed to check. We have 2 series. We did this, and the series on the right converges. That was 1 over n squared again. Oh, no, sorry. That was the geometric series, 1/2 to the n. So that one converges. So therefore, the AN series that we're looking at also converges. So I'll go back and write this over here as well. Okay, last little thing I'll say about the direct comparison test, zooming out here. As you can see, right, the workflow is a little different as compared to the limit comparison test, right? We did that in video 7.1. Throughout the course, we're going to be discussing when to use what test, how do you know, right? And the long answer, or the short answer of that long story is use the test that you are most comfortable with, that you can apply the fastest. Right? So for the direct comparison test, like we talked about, there's a lot of inequalities, right? So we're dealing with inequalities all the time here. You may not have dealt with inequalities a lot, or maybe it has been a long time since you've done that. Okay, so this is a skill that's going to come in real handy. You might want to work on that if you're going to be using the direct comparison test a lot. Great, thanks for watching.